The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.
Ben, it's time to get started with our super glue gun project.
Oh yeah!
What's the first step?
Okay, well, you bought a bunch of different brands of glue guns. We're gonna take them all apart and see which one of those is closest to what we want to build.
Cool.
And then once we find a pretty close glue gun, we're gonna kind of use it as inspiration.
Okay.
Then we're gonna take the heating element out of it, or maybe just leave it in. But what we wanna do is we also wanna work on controlling that. So in the original project, we used a solid state relay, which worked, but it's expensive. So we're gonna try controlling the temperature and the AC current with a triac, which is like a transistor, but for AC current. Let's get started.
Amazing hacks.
Should we take it for a spin?
Inspired designs.
Imhotep's priests.
Regrettable acting.
No one seems to get it.
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Well, Felix, it looks like we have a variety of glue guns here to take inspiration from.
Let's get inspired by taking these apart then.
Yeah, so just keep all the screws, you know, because we'll probably put them back together. But if we find one that seems to have a heating element that's close to what we want, maybe we can use that for our further tests. I bet these heating elements are like commodity parts we could find overseas. In the competitive world of high-stakes disassembly racing. You know, that kind of looks like the heating element from the last time we did this project. Oh good, thanks for the warning that the hot glue gun is hot. Does yours have a temperature control?
No, it's on off. Where's yours? Oh, right there.
Yeah, this one does. Up is hot. Okay, so I'll remember that. Up is hot because the sun is above us. Well, it's not really above us.
No spring.
Actually, it's to the side of us. Well, yeah. Do you think that makes sense? If we consider the orientation of the solar system,
Well,
like away from the disk is up.
if I want to see the sun, I have to look up. usually.
That's
So,
just up from your point of view, though.
Yeah, that's how I'm perceiving it.
Okay, let's compare these mechanisms. Well, this part looks pretty similar. It feels like it's like a silicon entry point. Yeah, yours has like a clasp around it. Is that holding the heating element in place?
I don't know what this is.
Oh yeah, I think it is. Whereas this one, there's like a barrel heating element. See that?
Oh, yeah,
Where
okay.
it just goes in. Oh, this has probably 2 windings to it. If I had to guess.
And you want to do like varying temperatures, right?
Yeah, I don't know if we necessarily, we probably don't need 2 windings. Yeah, see the switch here? So there's 2 colors, blue and white, and I don't think white means neutral like it usually does in AC.
Does it have on off?
It does not. So when you just have it on low, it would just use the white winding. And then when you flip the switch, it would also connect this white winding here with the blue winding, which would turn on 2 coils. So it's basically a double wound heating element. And so it's like, it either has one on or both on. So that's how it changes the temperature. And yours is just a single?
Yep.
Hey, you know what? If we hooked up a meter, we could get the resistance of the coil and then figure out how much current it will draw using Ohm's law. Okay, so the sticker said high is up. So that's low. Oh, okay. I realize this works a little differently than I thought. Okay, so this is the low setting, and see how it's connected, right? When you switch it to low, it's putting the 2 coils in series. Well, here, let's do this. We can go to resistance. We should be able to see a change. All right, it should be on low right now. Okay, switch it to high. Yeah, it looks like it doubles. Well, maybe it is turning on 2 windings. But we just want a single winding, right? Like 1 winding, and we pulse it to change the temperature.
Yeah.
It's kind of like the 3D printer works. I mean, really, the hot end is either on or off. It's just how long you leave it on or off is what changes the temperature.
Okay.
So that would require a solid state relay.
So I ripped the heating element out of this one.
Oh.
I just violently tore it out.
Well, that's what that clip is doing, right?
Yeah.
You could make like a whole sauna with this heating element. Well, it looks like it's just covered with Kapton tape. Should we take it apart further?
Yeah, sure.
Do it.
Wow, this is very brittle.
Oh, no, it broke?
Whatever this is.
What was in it?
This like some kind of ceramic thing that was in between these 2 metal plates. And then
What's this piece of metal here?
this is what was holding it in there. This plastic, or this spring was latched onto. This ceramic piece fell from like this high onto the table and like shattered. Very delicate.
I guess that one's a wash.
I'm gonna put it back together and see if it will heat up.
Well, yeah, it might. I mean, you're still pushing both sides of the ceramic, right? I'm gonna try to put this one back together too.
This one is warm and ready.
This was, looks like it was labeled incorrectly. I switched it to low and the temperature went up. That would explain the wiring.
Well, then,
Oh,
maybe,
China. Yeah, the sticker, I'm just confirming with the kilowatt, the sticker was backwards. Up is low and down is high. Okay, let's say you've got coils. Let's just say these glue stick represent coils, right? So these are the two coils, the two windings inside this glue gun. Now, if you pass the current through both of them, there's more resistance, which means it uses less current, which means it's cooler. But if you flip the switch and bypass one of them, current flows through just one, which makes it hotter. And that's the way it looked like it was wired when I took it apart, but it didn't make sense because that didn't match the sticker. But as we see here, the sticker was upside down. Well, it wasn't even upside down. It was printed like high-low. So it wasn't pasted on upside down. It was designed upside down.
That's quite impressive how that heating element is just those two tabs and the ceramic between them.
And all they're doing is passing 120 volts through it. What's the wattage of that?
20?
20 watts?
Yes.
Oh, hey, we could hook it up to the kilowatt and double check the math. Kilowatt tells you how much energy whatever is plugged into it is consuming. And there's just one setting on that, right?
Yep, off and on.
All right, 121 volts, 6.9 volt amps, 6.7 watts, 0.05 amps. So watts are volts times amps. So let's see, we take 120 times 0.05, 6. Yep, that pretty much matches up. That's not very much at all. So even though it says 20 watts, it's actually taking less than that. Of course, it could have to do with the voltage. Like if it was 110 volts times 0.05 amps, no, that wouldn't make a difference either. It's only drawing 50 milliamps at 121 volts. It's about 6 watts.
Did you get a reading on that thing?
Does it say what it is?
10.
120 at 10? Yeah, let's take a look. Of course, they could be listing the worst case scenarios. This one's actually closer to 10 than yours. It's starting to go down. You think maybe something got damaged?
Yeah. Well,
That
I don't think that's. I saw something become damaged.
Well, this one's only, because yours was rated at 20 watts. This one's 10 watts, and it's reading 7.1. It's not a huge difference. Although maybe you damaged the efficiency.
Well, you know what? I have
of
this
yours.
exact same.
Glue gun?
Yeah.
Oh, so we can do a control.
So this is exact same.
All right, so the one that's not been busted, let's see what it takes. It's definitely higher. Still not 20, it's like 9.5. Of course, voltages here in America vary. You can go from 110 to like 121. Like we're at 121 here. Okay, so this glue gun, which was very strangely shaped, I think is kind of like the closest to what we want to build that we've come across so far. Here are my reasons for thinking that. First of all, there's only a single winding, so one pair of wires that go to the heater block. And then there's another pair of wires going into it, which I believe is the thermistor. Then down here, the temperature control is done with a potentiometer, which is, kind of what we want to do. So we have this guy here. Let's see what it is. BT136, okay. Okay, it is a glass passivated triac.
Ah.
It says here, Felix, that the triac is the most commonly used semiconductor device for switching and power control of AC systems. The triac can be switched on by either a positive or negative gate pulse, regardless of the polarity of the AC supply at that time. So you can do it with thyristors as well, but the triac basically makes it a lot simpler. So the polarity doesn't really matter. I guess the next question would be, how do we control it with a DC logic circuit?
We need an optocoupler for that.
Ah, we have some, right?
Yes.
So it seems like an optocoupler designed for triacs along with a triac is going to be a much cheaper choice than a solid-state relay, which is probably just all of that put into one package.
Yeah.
All right, so maybe we should rig up a test circuit. So an optocoupler is a device with two separated elements. In this case, this side is going to, light up a little LED inside of it, and the other side will receive that signal and then allow current to flow. So we've electrically isolated the DC from the AC. So if this circuit's correct, when I flip the switch, this light should turn on. Yeah. All right, you ready?
Yeah.
Hey, it works. Well, let's see. How many watts is this?
I don't know.
13 watts. So yeah, this is in the ballpark of the hot glue element.
Yep.
Yeah.
Excellent.
Shall we put on something bigger? So, where did you hide the data of the Prime Minister and the pig? I'll never talk. Boy, Felix, all this talk of triacs and optocouplers makes me think we should probably do a block diagram of what's going to be in this glue gun.
All right.
I mean, we've talked about it, but we should like draw it.
There's a microcontroller.
MCU.
We have our 120 volts coming in, AC, transformer, and we have our bridge rectifier and our regulator.
Oh, on the inside of the microcontroller, I can draw what kind of port we need. ADC. I'll just put IO for that one.
Will the motor controller, will we need 2 lines or 4 lines going to the
We
motor?
need 2. The states will be one direction, another direction, brake, coast. Oh, and then we're talking about the zero crossing detector.
Okay, what do we need for that?
Another opto transistor. And then it would go to a general IO. This would be an interrupt control. So we connect that to an interrupt. So every time there's a zero crossing, we would use that as the base point for our PWM. So like if we have, okay, so like, right, AC, then point where it crosses the 0 voltage line,
Yeah.
zero crossing, right?
So our code then says, okay, when it's within here, we want to do our pulse width.
Yep. So if we, like in theory, like what if there was a pulse width that was kind of like this, like, right? Mm-hmm. If it was at exactly the wrong time, you would never get the full
We
power.
get exactly what we don't want.
Right. But if we can trigger our PWM to cycle at the zero crossing, well, this isn't really the best. Well, yeah, that would, you could cut half of it off if you did that. So what we'd probably do is it would that would be the starting point right there, and then you would vary from there.
Okay.
So it would be like that would be your PWM point. But anyway, yeah, I mean it would probably work without it. But if we did sync to the zero crossing, it would be the proper way to do it. This looks like a $1 trillion glue gun. I've been logging tests with this glue gun. So here's the glue gun on high, about 300 Fahrenheit. Then I hit it with the fan and dropped it down to 190. And also I got the thermistor reading from each one. Then I let it heat back up to what I assume would be the low setting, 230 Fahrenheit, 3.2 K. So now I'm gonna let it cool down to room temperature and then get another reading from the thermistor, and then we can figure out what the range is. So if this is like a 10K thermistor, that means, you know, the total range of what it can do is gonna be 10K. So when we do the circuit, we would draw it up like this. We'd have voltage here, then the thermistor there, then we'd have a sense point to the ADC there. Then we'd have another resistor going to ground, which would create a voltage divider. Probably, you know, well, it wouldn't have to be the same value, maybe like half the value. So if this is 10K, I mean, I honestly don't know. I just pulled a thermistor out of a bin. Let's say this is 5K. Because if we just hooked up the thermistor to the ADC, there's really no reference to ground, so we don't know what it is. So we need to see the balance. It's kind of like, in a way, hooking up a potentiometer to the ADC. So we have the thermistor on one side, that changes, a pull-down resistor on the other side that doesn't change, and then we can look at the difference using the ADC on the system. So what we can do is we can map these numbers to the 10-bit value coming out of the ADC and then approximate what the temperature is. And then we can control it. We can say, uh-oh, temperature, you're getting too high. I'm turning off your power until you get low again. Oh no, you've gotten too low. I'm turning on your power. Turn on your hot light. So we have these other thermistors here, and these actually have the bag and the text, 0 power resistance at 25 CK ohms. So this one would be a 10K thermistor, whereas the one we strapped onto this is probably about 100K thermistor. So we're looking at temperatures above room temperature, but we actually have a pretty good scale here. We have 4 data points. I think we can map that out and get a pretty good approximation of what our temperature is. Now we do have to take into account that this pull down resistor will change the value somewhat, but that shouldn't be too difficult to figure out. Cool, so what I'm gonna do next is I'm gonna hook this up to an ADC with a voltage divider and then connect the plug of the glue gun the same way we had the light bulb connected. Okay, I've hooked up the thermistor to the ADC on this Arduino, and then we have a 10K pull down on it. And we're getting a value of course, this is a 10-bit ADC, which means it's gonna go from 0 to 1023. Getting a value of roughly 76. Now don't get excited, even though that is room temperature, that's just a coincidence. So what we're gonna do is we're gonna write down, okay, with 120K resistance on the thermistor and then 10K on the pull down, so that's a voltage division, we have approximately the value of 75. So what we can do is, from our mapping before, we know that when we were at full temperature, we had about 1K resistance. So we can remove the hot glue gun and then stick in a 1K resistor to simulate that temperature. And now we get a new reading of 931. So we had 930. We could map above that. So yeah, now we have 1K and 10K. So if you think about it from a voltage division, we're much closer to the VCC than we are to the ground. And we could actually go a little bit higher than this, but I think this should be good for now. Again, I mean, if our final glue gun is more like 400 degrees, we'll need to scale it differently, but this is just a rough test to see how it all works. So now what we can do is we can take from 75 to 928 and map that in the Arduino software using the super easy to use map function. First, we get the temperature. We map the pin from 70 to 950, from 75 degrees to 300 degrees Fahrenheit. So if current temp is more than the target temp plus the dead zone, we turn off the triac to cool it off. If current temp is less than target temp minus dead zone, we turn the triac on. All right, let's upload this. It's actually already running. Well, it will be running here, but until I plug in the AC, nothing will happen. We have this old school Edison plug and then the socket here. So this little CFL should turn on when the glue gun does. So hopefully you can see the change. All right, so temperature 76, target 200 degrees, triac state is on. All right, so this will give us a status update as well. Okay, so when I plug this in, since it's below temperature, the light and the glue gun should turn on. So the triac state should turn to off once it goes past 210.
208, 209.
Here it comes.
210.
Bingo. Now it should start dropping. It might, well, it'll probably go up for a little bit more.
212.
Okay, and we should be able to extrude glue at this temperature. Oh yeah.
That's freaking cool.
Okay, we're down to 273, so it should trigger at 269. So now it's going to try to hover around 275. So it'll be a 10-degree range. I mean, we could probably tighten it up a little bit more. But I think it's better to let it, as long as we're within 10 degrees, I think we're okay. That's better than just pulsing the triac all the time. Or maybe it doesn't matter, I don't know. But the less we have to switch, seems like that's better in my case. Maybe it doesn't matter, I don't know. Of course, Felix, if we're not PWMing it, we don't have to worry about the zero crossing.
Oh, yeah.
I mean, this is literally like someone oh, my iron's too hot, unplug it. Oh, my iron's too cold, plug it back in. Oh, my iron's too hot, unplug it. Cool, well, I think if we do it this way, we can avoid the PWMing and the triac. That saves
30 cents?
Yeah, and a pin. Let's cost it all out. Cost it all out.
Let's recap. What have we done so far?
In today's episode, we took apart a bunch of glue guns, saw how they worked, then we picked one glue gun that would be easy for testing, and then we used a triac to control the AC current in the hot glue barrel, and then we also used a thermistor to sense its temperature. That allowed us to control the temperature at which it extruded glue.
That seems like good progress.
Yeah.
What's the next step?
Well, the next thing we're going to do is work on the extruder part. So we're going to try to find the smallest, cheapest DC gear motor that we can and try to push that glue through that barrel.
If you have any comments about the build so far or ideas for what we can do in the future, let us know on the Element 14 community on element14.com/TBHS.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. Oh no! The circuitry in my eyes that records everything I see! Can you feel the love tonight? No! This is how cavemen had to 3D print before they had 3D printers. Well, this could be like an episode of Black Mirror. It's like we have to design the ultimate project, but then you see the price of it change, and if we get past like $9, we explode.
Yeah, something terrible happens.
Yep.
Yeah, maybe not only like a stand that automatically retracts, but a stand that works.
It's so stupid when movies have transparent screens. It's like, that would suck. Yeah. So would Shark Boy and Lava Girl, would they be a thermal couple?
Okay.
I just want to get a Kiwi, a British person, and an Australian in the same room. Why not? It's like a joke. So there's a major storm front coming through here, and it's going to be sweeping up into the Midwest region and bringing some of the Arctic air down with it, and also Texas. Page pals! If people are watching telly, or on the loo, or if they're throwing rubbish into a bin on holiday, they're going to need page pals.
Are you watching the same thing as me? Of course I am. We both have page pals.
Page Pals is an innovative new service that links your computer's browser to other people's browsers. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.